Welcome. Let's take a look at an introduction to the net change theorem. If the integrand f of x of the definite integral from a to b of f of x is a rate of change of some quantity, then the integrand f of x is the derivative of some function, the antiderivative, or capital F of x. Then the definite integral can be rewritten using capital F prime of x in place of f of x as the integrand and evaluated via the fundamental theorem of calculus. That is, the integral from a to b of capital F prime of x dx will be capital F at b minus capital F at a. Or, if we find the antiderivative of this derivative, we will evaluate that at b minus the evaluation at a. So this definite integral gives us the change in the quantity that capital F of x represents on an interval from a to b. So let's take a look at a couple of examples to help us understand what this theorem's trying to communicate. So our first example is looking at v prime of t as the rate water is filling a pool. If v of t is the volume of the water measured in gallons in a swimming pool at time t, then its derivative, v prime of t, is the rate at which water flows into the pool at time t. So assuming that v of t is the volume of water and that v prime of t models how the rate at which water flows into the pool, then on an interval from t1 to t2, if we have the definite integral from t1 to t2 of v prime of t dt, that would equal the antiderivative of v prime of t is v of t. So, and I have a typo here. This should be v at t2 minus v at t1 is the change in the volume of the water in the pool from t1 minutes to t2 minutes. So keep in mind that this v of t2 is the volume of the pool at time 2, and v of t1 is the volume in the pool at t1. And so if I subtract and find the difference of those quantities, then that will give me the change in the volume of the water in the pool. Looking at a different scenario, let's look at bracket C prime of t as the rate of change of a chemical reaction. So just to remind you that when we write with the prime notation, this is conveying this idea that we have change in concentration over change in time. So if C of t is the concentration of a product from a chemical reaction measured in parts per million at time t, and time t is measured in seconds, then its derivative, C prime of t, is the rate at which the reaction is occurring. So on the interval of time t1 to t2, this definite integral from t1 to t2 would equal the antiderivative of C prime, which would be C, or the concentration, at T2 minus the concentration at T1. So this represents the change in concentration between those two times, or the change in concentration from T1 seconds to T2 seconds. Another example, let's assume that h prime of t is a rate of growth. So in that context, if h of t is the height of a child measured in millimeters at time t, and we're measuring in days, then its derivative dh dt is the rate at which the child is growing, measured in millimeters per day, at time t. Then on the interval of time t1 to t2, the definite integral from t1 to t2 of h prime of t dt would be the height at t2 minus the height at t1. So this represents the change in the height of the child, measured in millimeters, from t1 days to t2 days. So with that introduction, let's see if we can interpret a definite integral via the net change theorem. So if w prime of t is the rate of a puppy's growth in ounces per week, where t represents the number of weeks from birth, what does the integral from 0 to 2 of w prime of t dt represent? Well, our integrand here is w prime of t, so its antiderivative would then be w of t, and we would be evaluating that from t equals 0 weeks to t equals 2 weeks. And so that would be w at t equals 2 minus w at t equals 0. Now, notice that our rate was given to us in ounces per week. So the units of measure were clearly defined in terms of weeks. But what are the units of measure for W? Well, the units of measure for W are these ounces, because we can think of W prime of t as being dW dt, and t has units of measure of ounces, of weeks, and therefore W should have units of measure that are ounces in order for the rate we were given to make any sense. So W of 2 is the ounces that the puppy weighs at 2 weeks, and W at 0 is the ounces that the puppy weighed at birth. So W2 minus W at 0 should represent the change in the weight measured in ounces of the puppy during its first 2 weeks of life. Let's look at another example. If v of t is the velocity of a particle in centimeters per minute at time t, what does the definite integral from 0 to 14 of v of t dt represent? Well, we know that velocity is the derivative of position. And in this particular context, we know that the rate we're dealing with is centimeters, so position is measured in centimeters and time is measured in minutes. So this definite integral is the integral from 0 to 14. Instead of thinking of this as velocity function, let's think of it as s prime of t dt. And then the antiderivative of s prime of t would be s of t. And we need to evaluate that from t equals 0 minutes to t equals 14 minutes. And so this would be s at 14 minus s at 0. And so we have the difference in the position of the particle from 14 minutes minus the position of the particle at 0 minutes. So in this case, we have the displacement of the particle measured in centimeters after 14 seconds as measured from its position at 0 seconds. Let's look at one last example. We have a honeybee population that starts with 250 bees and increases at a rate of n prime of t bees per week. Write a definite integral that represents the total bee population after 12 weeks. So the population starts and increases at a rate of n prime of t bees per week. So n has units of bees and t has units of weeks. So, and we're interested in what happens after 12 weeks. So we're going to start measuring at some time, and we'll call that time t equals 0. That's when we'll start measuring. And we're going to be measuring again after 12 weeks. And we know that the bee population is growing at a rate of n prime of t dt. So this will tell us how the population grew over the 12 weeks. Okay, that's how the population grew. But we haven't yet incorporated the fact that this started with 250 bees. So we have a definite integral that represents how the population will grow, but we want to represent the total bee population. And that's actually rather easy. This is how many bees are going to grow within the population, and all we really need to do is add in the number of bees there were when we started. So we start with 250 bees, and that population is going to grow over the 12 weeks at a rate of n prime of t dt. I hope this has helped you understand the implications of the net change theorem.